Welcome everyone, and thank you for coming to today's session on functional Python for the ETL developer. I'm Joshua Higginbotham, and I'm the Data Services Manager for Republic Bank and Trust based out of Louisville, Kentucky. For today's session, we'll be covering a good deal of info, so if you have any questions, please feel free to post to the chat as I will be monitoring and answering questions throughout the session. This session will cover the various approaches to ETL that we see within the community now, why we chose Python as an additional tool to our ETL toolbox, and finally, a ton of demos that really show you the flexibility that you'll gain by adding Python to your toolset. ETL is not a new concept of business intelligence. In reality, most core functions within an organization, whether it's in IT or the business, leverages some form of ETL in their daily processing. As time goes on, this function within your organization will continue to grow, and we must find new ways or tools to adopt that will support the various needs or requirements that you will face. As a data professional and BI practitioner, you've probably worked with the majority of these below, BIM being probably the one that is newer to some individuals. All the items listed are great assets to bring into your ETL toolbox. Choosing one will be based off some various conditions. In the chart in front of us, I've listed out some of the conditions that I look for when adding such a tool. All the items listed I've worked with in some form or another over my years in IT. The columns that I've listed are based off my personal opinion and marked based off some of the needs that I required during my review. If you worked in SSIS long enough, you'll know some of the shortfalls to using a workbench style development tool. While these shortfalls are minimal, the advantage is that the learning curve can be minimal in comparison to the 3 scripting based languages you see below. One of the key determiners of what we chose in the end was based off its ability to scale to the cloud in a manner that would not lock us into a set product or language that would limit us in the end. So why Python? When I assumed my role within the organization, the first thing I took over was all of our ETL processes. I soon found out that the systems that our ETLs called were highly in flux. This caused a good deal of grief when handling schema change across multiple SDLC environments. We'd have packages deployed just fine in our dev, QA, and stage environments, just to get to production and fail due to a metadata issue. We also found that we had a good deal of project requests coming through that were similar in nature across the various platforms that we supported. We determined based off this that we needed something we could build a framework with. We initially started with BIML, but the learning curve was a bit tough, and we feared that as we approach cloud adoption, that BIML wouldn't be the tool for us in the future. So we set out to see what we could work with while on premises that would also scale to the cloud with minimal effort and change. Python ended up fitting that need as we could leverage it in all aspects of the BI platform in Azure and even spin up certain infrastructures using Python as a language. The benefit of Python is there is a wide assortment of projects within the community to support whatever function you may need. In ETL, we are predominantly going to work with 3 to 4 to facilitate the operations that we need. The first library that we're going to go over is the Pandas library. The Pandas library is going to be your best friend when it comes to ETL and Python. It's leveraged in many functions from data profiling, data access, and data manipulation. This library will be the basis of the majority of operations that we complete today. One of the key benefits to Pandas is its ability to read various non-structured data types. This becomes even more of a benefit when we start thinking about persisting data outside of a structured data set like SQL. When determining what non-structured data store you're going to use to persist your data, you may want to look at what is supported in the cloud adoption approach that you may be looking at. For us, the Parquet file was one of those files. We knew that Parquet files were supported both on premises and in the cloud. And in the cloud, we're going to start seeing Parquet leveraged in our Delta-based operations. In today's demos, we will go over how to create Parquet files, read those files, and what to do with them after you've created them. The next library that we're going to cover is SQL Alchemy. SQL Alchemy is an ORM or object relational mapper. You may know another ORM like Entity Framework, and you may also know a DBA that may look at you bad for even mentioning something like this. But with anything, if it's used in the right form, it can be beneficial without causing undue stress to our environments. With SQL Alchemy, we will be able to leverage this library to support connecting to SQL Server, as well as have the ability to support additional database types, if so needed. For a list of these databases, you can go to SQL Alchemy's documentation and find the syntax or code to cover how to connect and query these systems. In today's demos, we will leverage SQL Alchemy in conjunction with our next library, PYODBC, to access our SQL Server data stores, to pull data, to be able to do some form of ETL operation. The last library that we're going to cover is PYODBC. PYODBC is an open source project for accessing ODBC-based databases. In our case today, we will be using this to access SQL Server, used in conjunction with SQL Alchemy. This can be used on its own if an ORM is not ideal or not approved by your organization. In today's demos, we're going to cover common ETL patterns with Python. We're going to start off easy, leveraging pandas to show you how we can read non-structured data. We'll then bring in our SQL Alchemy and PYODBC libraries to show you how we can read structured data. While this is a good start, a great developer is more than just the ability to write code. In fact, a great developer is always thinking of new ways to get out of writing code. With this thought, we will introduce functions and classes to support common ETL patterns. In today's demos, we're going to be using Microsoft's Visual Studio Code, or VS Code, for our development environment. And you'll notice that we already have a handful of scripts that have been written. Within our scripts, we have Python notebooks, or Jupyter notebooks as you may know them, Python scripts, a requirements.txt file, as well as some folder structures that store classes, configurations, and a folder that acts as our file storage for both incoming and outgoing files. In our first demo, we're going to be using a Python notebook to connect to non-structured data. A notebook supports both Markdown as well as regular code, depending on what kernel you're using. In this case, we're using the Python kernel to build a nice readable document that we can execute in a linear fashion or all together. The first thing that we're going to do is we're going to import any libraries that we need to support this script. First off, we're going to import the pandas library. We're going to alias it as PD. To run a cell, we can hit Control Enter, and once it is ran, you'll have a numeric identifier which tells you that this was executed successfully. We can then run the below cell, which will read a CSV file that sits in our file storage incoming directory called factsales_export.csv. In this code cell, we're calling the PD, pandas library, read_CSV function, passing in the location to where the CSV file is stored. And we're loading it to the data frame called df_CSV. Once it has been read, we are going to print it to console using the df_CSV, the data frame that we called above, with the head function. Head basically lists the top 5 rows that are available in this data frame. We run this and we see the first 5 rows of our data frame. To condense this, you'll see that it drops down to a new line as additional columns come in range that do not fit within the one row of the console. So we see our columns, product key, order date key, all the way down. We can look at the data within. We see that the output also lists that we have 5 rows. So these are the 5 rows that were outputted. And the data frame is 29 columns in width. The output of this doesn't mean that we only have 5 rows in our data frame. To prove this, we can insert a new cell below. We can call our print function. We're going to pass in our data frame, df_CSV. We can call the shape function, passing in a 0 or a 1, 0 being rows, 1 being columns, and output it to console. We see that we have 60,398 rows available within our data frame. Take a look at our columns to verify that it is 29 in length or width. We can call this same print function, df_CSV dot shape 1 We see that we do have 29 columns available within our data frame. As an ETL developer, you're probably used to calling many different data sources, whether it's non-structured or structured data. And you'll realize pretty quickly that not all structures are as performant as others. Excel files being one that tends to take a little bit longer to read. If we execute this cell, and while we're waiting for it to load, we can see that the same language to call this function is similar to what we did with CSV. We define our data frame that we want this data loaded to, call our PD pandas library, passing in the read Excel function and the location to the file where it's located. And we'll do the same print data frame head call, which will then list out the top 5 rows of our data frame. We'll see that the data is similar in nature, 5 rows by 29 columns, and it took a little bit longer to read. When we start talking about persisting our data in non-structured data files, determining which file type to use is going to be important when trying to scale our solutions. The benefit to pandas is that calling non-structured data is similar in nature, regardless of whether you're calling a CSV file, an Excel file, a pickle file, feather, or parquet. It's predominantly read all the same. There are various options that may differ, pickled files being one of them, because they are compressed files, and you need to know the compression algorithm that was used to create that pickle file. We'll continue on and we'll run our other cells that define calls to additional non-structured data files and load them to a data frame. So in this cell, we see that we're going to call a feather file that's stored in our incoming directory and output it through head to display the same results. So we see 5 rows by 29. And then here is our pickle file. And like stated before, with pickle files, we need to know what level of compression was used. So this is an additional optional parameter that we need to call and pass in the gzip compression algorithm to be able to read this. Lastly, we'll read a parquet file, and you'll again notice that all the different calls that we made, regardless of the file type, it was all read the same, minus again that pickle file where we had to add in the compression algorithm. If we want to take a look at what the file size of each of these files were in comparison to the data that was stored in it, we can right-click our file storage, go Reveal in File Explorer, go to the directory, and we see the different file sizes of these individual files based off of the file type that we have. So you'll notice that the CSV file type takes up more space than all others, followed by the Excel file, then the feather file, then the parquet file, and the pickle being the smallest. The reason the pickle file is the smallest is again because of the compression rate that we have using the gzip option. So now that we've discussed reading non-structured data, the next step that we need to cover is connecting to SQL Server and reading data from a table. So we have another notebook. This notebook is similar in nature to what we saw in the non-structured. We're going to import some libraries. So in addition to the pandas library, we're going to use the PYODBC library. We then need to define a connection string. In this case, we're going to define a dictionary called source_db_config to store values that relate to a connection string that you've probably seen before. We're going to pass in a trusted connection, meaning use the Windows authentication, the Windows account that I am, which is Josh. We're going to use the driver SQL Server. I'm calling our local host, the database AdventureWorks Data Warehouse 2017, and we're going to auto commit any transactions. We then define our SQL query that we're going to use in our call. So we're going to select all the records, then create an order year date or order year column, order month column, order day column. And all this is doing is taking this query and putting it into a string called SQL_query. We then need to set the connection. So we're going to create a source connection variable. We're going to call the SQL, which is the PYODBC library, .connect, and then we need to pass in the connection string. By passing in 2 asterisks before the dictionary, we flatten that record into a singular string, and then we call the pandas pd.read underscore SQL function. We pass in the SQL query we're going to use to pull back data and our source connection. We're going to load it into a data frame called df and then print the data frame to console. We see from the output the data that was returned. We can scroll down to take a look that we have 60,398 rows by 29 columns. Once your data has been extracted, regardless of whether it's non-structured or structured data, we're going to want to look at our data types of our data frame to see, are these data types what we want for our next phase of the ETL? So to look at our data types, we can hit this plus sign to create a new cell, call the print function. We're going to pass in our data frame, and then we're going to call dtype, or dtypes. Control Enter to run the cell, and we see our columns as well as the data types that belong to those columns. These are data types that correlate to a pandas data type. So you will have to do some level of translation if you're used to a SQL data type. If you go to the pandas documentation, you can see what these are and what they correlate to. When working with non-structured data files, one concern that we have is that the data types are not inherited or stored within the file. So when working with CSV files, we may have to define the data type after we have read this file. That way we are transforming the data types prior to moving into the transformation where we may be joining to another data type. There are certain functions within pandas, certain transformation logic that will not work if you try to join off one data type that does not match to another data type. Now that we have covered connecting to non-structured and structured data, we're going to go into an area of code reuse and scalability. In Python, we can leverage object-oriented programming practices that you see in C# and VB.NET, where we define classes and functions for code reuse. Within these classes, you'll see we have a folder called classes with Python files that store the individual class and function needed to facilitate whatever process that we're looking at. So we have a class called extracts, one for load, one for SQL, and one for transforms. The first one that we're going to look at is a SQL class. We're going to define the libraries that we need to import. Then anything that we need to call from those libraries to be able to facilitate some operation within our process. We then define what the class name is. So we're going to define the class SQL. We're going to define an initialization of parameters or variables for this class. This will allow us to pass in variables with values related to the query and the connection needed for any function within this class. We then have a function called createConnection, where we create an engine using the SQL Alchemy library, passing in the connections that's defining the string for our SQL server, establish a connection, and then we return that connection to our main Python file. We then have another function for reading SQL. This is similar to the read function that we saw in the connecting to structured Python notebook, where we call pandas.read underscore SQL query, passing in the query that we define and pass into this class and function and the connection string. And then lastly, we return that data frame to our main Python file. We can define additional classes and functions for various levels of operation within our program. So we'll come look at our extracts class. Same thing, we'll define any imports that we need, the class name, any initialization variables that we have. We're going to define a function for reading CSV files, another one for reading Excel files. This is similar to the same calls that you saw in the connecting to non-structured Python file before. In the loads, we have an initialization of variables as such. Then we have various functions that send to the different data files that you see in the non-structured area. So we have one for sending to CSV, Excel, Parquet, Feather, and Pickle. And then lastly, we have a class for our transforms. There are certain times that you may need to step outside of a class or a function because the type of transformation you were doing is a one-off. There are some things that you just cannot build a function around, and that is okay. But for anything that is a common process within your system, like in here, we have a function that transforms the state field. So in ETLs, you may receive various versions of a state code, whether it's the char2 state code, the numeric state code, or something in the middle that you have to translate based off of a lookup table or a lookup file. So this is a way of defining a reusable function that will do that. You'll see that this is a join logic. So we call pandas.merge. We then give it the left, which is our data set, then our right data set, which we pass in as a param0, and then we give it the column that we're going to join on, where we pass in for param1. We then tell it how we want it to join. This accepts all the different join criteria that you see within SQL. So inner, outer, left, right, and such. And then we return that final data frame from that join back to our main Python file. So to take a look at how these functions are leveraged, we've got a couple Python files, one for each of these extract types. So we have a main underscore extract underscore CSV Python file. We need to first pull in some of these files to gather info. So to import a file that is internal to your project, we can call from, and then the file path to that. So we're saying go to the queries folder, the ADW underscore queries file, and we're going to import everything within that. Same thing for our classes. So we're going to import the classes.loads, and we're going to import the load class. Then classes SQL, import SQL. And then we're going to import any libraries that we need to facilitate this ETL. So we're going to import pandas, sys, which allows us to pass in parameters. So in a production environment, what we will leverage is this sys.argv1, which tells that this is the first input parameter. This can be passed in through a SQL agent job. So when we talk about automation, we can use this in our call from the job to pass in the extract name that is used here. This is how we can build a reusable extract logic for CSV files. Is all you have to do is change the extract name, as well as you can make this dynamic where you're calling individual queries instead of a defined query in here. We then need to pass in a config. So a config file is similar to an environment.config. There are different ways to do this. You can use JSON files, XML files, but in this case we're doing an INI file. You see that we have this INN file sitting in a config folder, which is here. Within the config.ini, we'll see that we have our environment. So this is where we could define the environment level variables or parameters based off of the SDLC environment that we're working in, whether it's dev, QA, or production. We then define our connection string based off this, the location to where the extract is going to go. We then need to define our connection variables. So in this line, what we're doing is we're telling what the variables that we're going to initialize the SQL class with. So as you saw before, we're going to pass in two variables. We're passing in an empty variable here because for our create connection, we do not need something in this area. We then define the connection string that we need to create this connection. We then set our connection based off of these variables, calling the create connection function within the SQL class. We'll then define our SQL variables for the read underscore SQL function. So we're going to pass in the fact cells underscore query, our connection string. And then once that call is made, we're going to load the data to the sales df data frame. After we've called this, we're then going to define our load variables, passing in the sales data frame, give it our extract path to where we want this part, our extract name, so the file name for this, and then we're going to call our function to extract this data into our extract path. To see how this runs, we can debug our solution or our script. To create a debug or a breakpoint, we can go to the line that we want to set our breakpoint at, select it, which will set our breakpoint. We can go to either the run option in the far left pane and run and debug, or you can hit F5 and it'll do the same. So we'll run our Python file, allow it to get to the breakpoint, and then we can step through our code and see what it's doing. So we've defined an extract name. We've defined our config value, read our config, and stored it. We're then going to define our connection. So if we hover over, we can see that we've defined our connection string as such. We're going to go to the AdventureWorks 2017 database on our local host using the SQL Server driver and a trusted connection of true. We're then going to define our extract path, which is our file storage folder and our out directory. We'll then define our connection variables. So as we step through here, you'll see that it goes into our SQL class and it initializes our variables for query and connection. We'll then create this connection, which will then call the function create connection, passing in our variables. If we hover over, we'll see that we have certain values like our driver is PYODBC, as well as MS SQL. We're going to return our connection, so then we can use it for our SQL variables. We're going to initialize the SQL class again with our query and connection. Call the read SQL function, using our query and connection to load a data frame, and then return that data frame to our main script. Once our once our data frame is loaded, we're going to call our send to CSV function, initialize it, and then send it to CSV through our send to CSV function. We see that output directory is going to be file storage out with a file name of test.csv, and we're not going to include the index in the data frame. So the index in a data frame is a 0, 1, 2, 3, 4 ordered type list, and when you output to a non-structured data file and you include it, it will show up as a column or cell within your file. So we do not want to include that in our extract. Complete this out. Then we can go back to our Explorer, go to File Storage, go out, and we see we have our test CSV file. So now that we have our test.csv file, we can look at the additional classes that have been defined that will load files for CSV, Excel, Feather, Parquet, and Pickle. Before I do that, I'm going to delete these files. We'll then rerun our CSV function, or sorry, our extract the CSV script. We remove the breakpoint. We now have our test CSV file in our out directory. We can open up our Excel file, which is similar to what we saw before, except that we are defining our extract name with a XLSX extension. We're going to then call the send to Excel file at the end to pass it into an Excel file. And just like reading data files, you'll notice that the Excel file to generate takes a little bit longer than what we saw with our CSV file. You're going to want to factor this in when you're starting to talk about persisting files. So an Excel file or even a CSV file, because of its limitations with data types, may not be the best file type to use when persisting data. And as you can see, it is still trying to output this data to this Excel file into our out directory. Now that that is completed, we'll move on to our Feather file. Same thing. You'll notice that the extract name has changed to test.feather. We're going to call the send to feather function within the loads class. We now have our test.feather file within our out directory. We'll call our Parquet file script. And lastly, our Pickle. So now that we have all of our non-structured files created, you'll notice that all of our main _extract Python scripts were identical other than these two areas, extract name and where we were sending it to. These things can be created in a way that they're dynamic and even passed in through some argument from the command line. Again, with pickle files, we have to define the compression algorithm that we're going to use. And you'll notice that in the classes loads class, that under the send to pickle, we define that compression. This again could be passed in through some argument or variable, kind of like what we see in our transforms class, where we have defined some filler variables that will allow us to make this a little bit more dynamic without having to hard code those values. So now that we've gone over some of the ways that we can build classes and functions, we want to look at what is something in the real world kind of used. So now that we've covered how to leverage classes and functions for code reuse, we're going to cover something that we may see in production. So in ETL processing, in data analysis, the first thing that we want to do is we want to profile our data. So profiling is a certain technique that I think is scarce within certain organizations, especially in their ETL groups. So now that we have covered how to leverage classes and functions for code reuse, we're going to review some common. So now that we have covered how to leverage classes and functions for code reuse and to make sure that our code is scalable for production environments, we're going to go over something that you may see in a production environment. Before we want to move into the actual ETL process, the first thing that we want to do is profile our data. Data profiling is an important step to the ETL process. Even if you're not used to it, this is a practice that you should pick up, as it's best to look at what your data is before you start the extraction and transformation and loading process. The transformation process is going to be tied heavily to that data profile. And we should be continually profiling our data as time goes on, because those source systems do shift, and our transformation logic that worked before may not cover all the edge cases that we find. So to profile our data today, we're going to use this profiling data notebook. We're going to import the libraries that we're going to use for this. So we're going to import pandas, NumPy, SQL Alchemy, and config parser. We're then going to call our SQL class. So one of the benefits is that anything contained within our folder, our project for Python, we can leverage. So now that we've covered classes and functions, there's no need to redefine our connection strings and all the logic to connect to SQL. I can reuse that same class that we use in our Python files to then use this notebook to be able to profile data within SQL. We'll define our configurations. From that configuration, we're going to set our connection string, define our connections to SQL, our variables that will define our connection to SQL, and create that connection. We'll define our query, select star from AdventureWorks 2017.sales.sales order header. We're going to read SQL query. We're going to call pandas.read_SQL_query, passing in our query string, our connection string, and outputting that into a data frame. We can then go get a count of all the records that are within our data frame, calling the dataframe.count function. So this is one of the first things that I always check when I'm importing data that I've never looked at before. I can see what are our value counts across each column, and immediately I'm starting to see that we're missing some data. So we only have 3,800 purchase order numbers, only 3,806 salesperson IDs, and then there's certain areas that we're missing. So we see that we have our credit card ID that we're not matching to the 31465 that we see above across the board. So that may be an indicator that there are certain orders that were purchased with cash or some other means. We see our currency rate ID is 13976. That may be important when defining certain reports around taxes and such. Because if this order was done somewhere outside of the country that the company was based in, they may have to handle taxes differently. And then we see that we have 0 comments related to these sales orders. We may want to look, are we receiving this data? Is there an issue that is causing the comment to be empty? This may be pertinent info in a reporting sense for sentiment analysis around the orders themselves. We can then go get how many columns that are missing values by calling the data frame is null function and then summing the values or summing the records. So this matches up to what we saw above. We're missing a little over 27,000 purchase orders, salesperson IDs. About 1,131 look to be maybe cash payments. And then we're missing all of our comments. We can then create a new column within our data frame to define to verify that these credit card IDs could be cash payments. What we can do is we can define a new column within our data frame called payment method. We're going to call our NumPy library to filter our data set where the data frame column credit card ID is null. If it is true, we're going to create a value of cash. If not, we're going to set the value to card. We can then print our data frame to view these records. One of the benefits to a Python notebook is that we can view and display the results in a different manner than print data frame.head. In VS Code, to view a data frame in a grid, you can go to the Show Variables Active in the Jupyter kernel, which will show you all the variables that have been defined and what values are stored. We see within this that we have our data frame DF, and there's an option to show variable in a data viewer. We select that option, and it will load our data frame into a grid-based design, kind of like what we see in Excel. So now that we've created our new field, I can see that we have our payment method of card. I can filter our rows. By the column. And I can verify that all the cash columns do not have a credit card authorization or credit card approval code to fulfill the thought that this is probably a cash payment within this order system. So now that we've gone over some common profiling concepts, we're going to go over a simple requirement that we have. The requirement is that we are receiving a list of breweries within the United States. We need to import this file and do some level of cleansing and then output that file back into some non-structured data set. So the first thing we're going to do is we're going to import this file. This file has been dropped off in our file storage in directory, and it's the breweries.csv file. We're going to define a new data frame. We're going to call the pandas function read_CSV. Then we're going to pass in our file path, a file storage in breweries.csv. We're going to name this df brew, as we already have a data frame in this notebook called df. We're going to do Control Enter, and we'll go through the variable data viewer to take a look at our data that was passed in. So we see that our CSV file has a column for categories, the latitude and longitude of the location of the brewery, the name of the brewery, phone numbers, postal codes, a key value, and websites. So as we're looking at this data and we're seeing that we need to perform some level of ETL on this. We notice that within the key column that we have our country code, a numeric code, Austin, or the city that this brewery is in, as well as a street address. Within the requirements of our change, we've been told that the numeric code here is our numeric state code, but the business needs this translated into the char2 state code, as well as if they could get the full state value, they would like it within their feed. We'll exit our data viewer to go back to our profiling. And then we see that we also have a state underscore list CSV file. So in the thought of having to transform this and build a scrubbed state code, we can import this state underscore list CSV file that is a list of all the states in the US, as well as their char2 state code and their numeric state value. We'll define a new data frame called df states, and we'll read this to using the pandas function for read CSV. Define the path to this file. Control Enter. Within viewing this, we see that we have our state name in a column, our state char2 code in a column, and our state number value within a column. So this is the beginnings of a means to transform that state number into either the state code or the state value. We'll do a quick profiling of our data. So let's go get our counts. So we see that we have 73, 74 categories with a matching key value. So we at least have a country code, state, city, and street for every one of our breweries. We have 73, 74 breweries. We do see that we are missing some phone numbers as well as a little bit of our postal codes. This postal code can be determined either through the latitude and longitude, which we show is missing, but then we could also try to infer that through our key value once we have split that out. We are missing a good deal of websites, but that isn't important for whatever we're working with. Let's go take a look at our data types. So we can see that we have the majority sitting in objects and the rest for latitude and longitude in a decimal value or float 64. We'll do the same check for our state list. And we see that we have all the values needed across those three columns. Our state is an object, state code is object, and the state number is integer 64. This may be important if we're looking for a leading zero in our join criteria. So you may have to do some conversions depending on how you're joining with this value. If the right side ends up being stored in an object data type with a leading zero. So now that we've profiled our data, done at least a little bit of a look at it, we're going to go to our pulling it all together Python file, which is, I know, a goofy name. We're going to go ahead and pull in our classes that we defined before. So we're going to pull in our extracts class, our transforms class, our loads class. We're going to import the pandas library. We're going to define a couple variables for our extract path, the location to our breweries file, our state list file, as well as where we're going to store the file once we're done cleaning and transforming it. These variables would be stored in our config file above, which we'll change out at the end. We're then going to define the variables needed for our extract class, passing in the extract path. We're going to call the read CSV file function and load it to a data frame. We're then going to perform a transformation. That transformation is going to do a split columns of our first data frame. The key column, which we noticed that had our country code, our numeric state code, our city, and our street address. We see those values are separated by a forward slash, so we're going to pass that in as the delimiter if you want. And we're going to load our second data frame with that. Once that data frame is loaded, we're going to want to rename the columns that were created during that split function. We're going to rename the 0 column to country code, 1 to state number, 2 to city, 3 to street address. We're then going to perform a merge operation, joining our data frame 1, which is our breweries list, to our second data frame, which is our data frame with our split values. And we're going to join off the left index and our right index. We're going to store the results of this into a results data frame. We're then going to change our state number field or column to a numeric data type, passing in the results state number column from our results data frame. So this is our first look at how to convert from one data type to another with a pandas function. We're then going to create an extract by calling our read underscore CSV file. Then we're going to do another transformation where we're going to do a transformation on the state. We're going to pass into our transforms class our results data frame, our state codes data frame, and then we're going to pass in the column that we're doing the transformation on, which is our state number column. We'll then load a final data frame using those values. We'll then call our send to CSV function within our loads class, passing in the final data frame, setting our output path with a test.csv file name. Before I run this, I'm going to clear out our test CSV. We're going to set a breakpoint at the start of our script to see how this runs. Move through our variables. We see that those have been filled with the string values that we passed in. Initialize our variables within the extracts class. Call our read CSV function within the extracts class. Our data source being the breweries.csv file. We're then going to pass in our transform variables. And we're going to call the split columns function within our transforms class to create a new data frame called the EF2. We see that we passed in our data set from before with the first parameter being key, which is a column that we're going to do the split on. We're going to perform the split based off of the forward slash within the string. and then we're going to return the results to a data frame. We're then going to perform a rename of those columns. We're then going to perform a merge statement or a join, in this case, off those two data frames to form a singular data frame called results. Convert the state number column to a numeric column. Then define an extract. Which will then read the state list CSV file from our file store. So then we can do a join to switch out our data types or our columns, with the state value that the business is looking for. We're going to perform our merge based off of our first data frame, which is the results data frame, and our state code data frame. We're going to join on the state number, and we're going to perform an inner join, making sure that the value from results matches completely with the value found in the state list data frame. We're then going to call a send to CSV function within our loads class, which will then output our final file to our out directory for the business to pick up. We can go into our out directory to take a look at our test.csv. To look at this a little bit easier, I'm going to reveal this in File Explorer, and I'm going to open it up in Excel. If we expand this out, we have our categories, latitude, longitude, the name, phone, postal code, the original key value, but now we see that we have our country code column, our state number code, the city, and the street address. We then have a 4, 5, and 6 column that we could delete to clean this up a little bit further, which we could do through Python. And we see that we have a state of Texas and a state code of TX for Texas. We can look at this and see that we have all of our state numbers matching to what we assume is Texas and Texas. We can verify this by looking that all of our 48s match to this, as well as our state number, or state and state code. And then we can peer down a little bit further, see that we're seeing some change within that to verify this as well. And that all of our state values match up. As we end, I want to say thank you to Microsoft for supporting the Data Platform Geeks and SQL Server Geeks community initiatives. I'll be hanging out for the next little bit to answer any questions in the chat before the next session. So feel free to reach out there and I'll be happy to help. Before we leave, remember there are prizes to win. You can post a selfie with the hashtag DPS2020, give session and conference feedback, or visit the sponsor and exhibitors at the conference. Thank you all.